For nearly all of human history, we looked up at the stars and asked one fundamental question: are we alone in this vast, silent ocean? Our ancestors saw the stars as gods or unreachable fires. But the idea of other Earths was nothing more than a poetic fantasy. Even as our telescopes grew, the planets of other stars remained hidden, drowned out by the blinding light of their own suns. Finding a planet is like trying to spot a firefly crawling next to a stadium floodlight, from 3,000 miles away. As late as the early 1990s, the official count of confirmed planets outside our solar system was exactly 0. Then came 1995. At a quiet observatory in France, Michel Mayor and Didier Queloz weren't just looking for stars, they were looking for a wobble. They found 51 Pegasi b, a gas giant half the mass of Jupiter, orbiting its star in just 4 days. This was impossible according to every theory. It was a hot Jupiter, a world so close to its furnace of a sun that its very atmosphere was boiling away into space. This discovery eventually won the Nobel Prize in 2019, because it proved one thing: the universe was crowded after all. But how do you find a tiny rock in the dark? You don't look for the planet itself. You look for its fingerprints on the star. Method 1, the radial velocity method. As a planet orbits, its gravity tugs on the star, making it perform a tiny, rhythmic dance. This wobble shifts the star's light. Toward us, it turns blue. Away from us, it turns red. This is the cosmic Doppler effect. Method 2, the transit. This is simpler. We watch and wait for a planet to pass in front of its star, casting a tiny shadow. By measuring that tiny dip in brightness, we can calculate the planet's size. It's like seeing a mosquito fly across a searchlight. With these tools, we launched a hunter that would change our history forever: the Kepler Space Telescope. Before Kepler launched in 2009, we were like people looking through a keyhole. We knew planets existed, but we had no idea how common they were. Kepler didn't look everywhere. It stared at one single patch of sky, monitoring 150,000 stars simultaneously, 24 hours a day, for years. It was waiting for the transit, that tiny flicker when a planet crosses its star. It was a game of extreme patience and incredible precision. The data began to flood in. 10 planets. 100. 1,000. Kepler revealed that there are more planets in our galaxy than there are stars. But these weren't all Earths. We found lava worlds like Kepler 10b, where it rains liquid rock and the surface is a molten nightmare. We found water worlds covered in oceans hundreds of miles deep, and frozen giants where the very air is turned to ice. Nature's imagination was far wilder than ours. But among this chaotic variety, the hunters were looking for something very specific. The habitable zone. The Goldilocks region where it's not too hot, and not too cold, for liquid water to exist on the surface. Kepler's data led to a shocking statistical conclusion: 1 in 5 Sun-like stars likely has an Earth-sized planet in its habitable zone. In our Milky Way alone, that means there could be as many as 40 billion potentially habitable worlds. 40 billion chances for life. But finding a candidate is only the beginning. Most of these worlds orbit stars very different from our own Sun, like red dwarfs. Red dwarfs are the most common stars in the universe. They are small and cool, but they are also temperamental, lashing out with deadly flares. If a planet is too close, these flares could strip away its atmosphere, leaving it a dry, radiation-soaked husk. No place for a fox. But then, we found a system that challenged everything we knew. A miniature solar system, packed with 7 rocky sisters. This is TRAPPIST-1. And it's the closest thing we've ever found to a cosmic neighborhood of potential Earths. To find these worlds, we have to be cosmic detectives. Since planets don't emit their own light, we must look for the clues they leave behind. First, the wobble, or radial velocity. Even a small planet has gravity. As it orbits, it pulls its star in a tiny, circular dance. This movement shifts the star's light spectrum. Blue as it moves toward us, red as it moves away. We call this the Doppler effect. Modern instruments like HARPS can detect a star moving at just 1 meter per second, the speed of a person walking from light years away. Then there is the shadow, the transit method. When a planet passes in front of its star, the light we receive dips by a tiny fraction. For an Earth-sized planet, that dip is just 0.01%. It's like watching a mosquito fly across a car headlight from miles away. By measuring how long the transit lasts, we can tell exactly how far the planet is from its sun, and if it might have liquid water. But some planets are too far for transits. For those, we use gravitational microlensing, using the star's own gravity as a giant lens. As Einstein predicted, gravity bends light. If a planet is present, it adds a tiny extra bump to the magnification. A cosmic magnifying glass. And then there is direct imaging, actually taking a photo. This is incredibly hard, like trying to see a candle next to a forest fire. We use a coronagraph to block the star's blinding light, revealing the faint glow of the planets hidden in the glare. But the newest and most exciting tool isn't about finding the planet, it's about tasting its air. This is spectroscopy. As starlight filters through a planet's atmosphere, gases like oxygen, methane, or CO2 leave their unique chemical fingerprints. With the James Webb Space Telescope, we are no longer just counting worlds. We are beginning to read their stories, written in the light. Armed with these tools, we've found things we never expected. Worlds that shouldn't exist. It's time to visit the exotic zoo of the cosmos.
Wow,
for centuries, we didn't know if our solar system was a miracle or a common occurrence. Then came 2009, and the launch of Kepler. Kepler was a staring machine. It pointed at one tiny patch of sky in the Cygnus constellation and never looked away for 4 straight years. It monitored over 150,000 stars simultaneously, waiting for the split-second dip of a planet's shadow. The mission was led by William Barucki. For decades, he fought for this idea when everyone else thought it was impossible to see planets from space. What Kepler found shattered our statistics. It discovered that planets are everywhere. There are more planets in the Milky Way than there are stars. Suddenly, the census of the universe changed. Most stars, it turns out, have at least one planet. The Great Silence was actually a crowded room. But these worlds weren't all friendly. We found Kepler 10b, lava world where the surface is molten and it rains liquid rock. And 55 Cancri e, a planet so rich in carbon and under such pressure that its interior could be made of solid diamond. Kepler showed us that nature's imagination is far wilder than our own. It wasn't just finding Earths, it was finding everything else. The biggest prize, however, was the habitable zone. That perfect distance where a planet can hold on to liquid water and life. The statistics are breathtaking. According to Kepler's final data, 1 in 5 Sun-like stars has an Earth-sized planet in its habitable zone. In our galaxy alone, that means 40 billion potentially habitable worlds. 40 billion chances for evolution to take root. But there was a problem. Kepler was too far away to see the air of these worlds. It could tell us they were there, but not what they were like. To taste the atmosphere of an alien world, we needed a new hunter. One with golden eyes that could see in infrared. The era of the census was over. The era of the characterization had begun. Let's look at the worlds that shouldn't exist. Our search for Earth 2.0 led us to a shocking realization: our solar system is actually quite boring. The universe is a gallery of the impossible. Meet WASP-39b. A world tidally locked to its star. On the day side, temperatures soar to 2,400 degrees Celsius, hot enough to vaporize iron. But on the night side, it cools down. The vaporized iron condenses and falls as a literal rain of molten liquid metal. Imagine that. Then there is 55 Cancri e. A planet so dense and carbon-rich that scientists hypothesize at least a third of its mass could be pure diamond. A world of treasure that would crash every economy on Earth. But you couldn't breathe there, and the pressure would crush you instantly. If you think Saturn's rings are impressive, look at J1407b. Its ring system is 200 times larger. If it replaced Saturn, we'd see it from Earth as large as the Moon. And then there's HD 189733b. It looks like a peaceful blue marble from a distance, but that blue color comes from silicate particles in its atmosphere. It rains glass here. Sideways. In winds reaching 7,000 kilometers per hour. It is a world of a trillion flying daggers. Not all planets have stars. We've discovered rogue planets, lonely worlds cast out of their home systems, wandering the freezing void alone. There could be billions of these orphans in our galaxy. Some might even have internal heat, keeping oceans liquid under miles of ice. And for the fans of Star Wars, Tatooine is real. Kepler 16b is a circumbinary planet, meaning it orbits 2 stars instead of 1. Watching a double sunset on a world like this would be a reminder of how diverse the architecture of the cosmos can be. The most extreme is probably the zombie planets. Worlds orbiting pulsars, the spinning corpses of dead stars that blast them with radiation. These were actually the very first exoplanets ever found in 1992. Planets born from the ashes of a supernova. Life here is almost impossible. But among all these horrors and wonders, we are still looking for that one specific shade of blue. The search for a habitable home. To find life as we know it, we follow the most precious substance in the universe, liquid water. Not ice, not steam, but the liquid stuff of life. This requires a perfect balance of distance and temperature. We call this the habitable zone, or more famously, the Goldilocks zone. Like the old fairy tale, it can't be too hot, where oceans boil away, and it can't be too cold, where everything turns to a frozen wasteland. In our own system, Venus is too hot, Mars is too cold, and Earth is just right. But the boundaries of this zone are constantly shifting. It all depends on the star. A giant, hot star has a Goldilocks zone pushed far out into the dark. Stay too close, and you're incinerated. But most stars in the galaxy are red dwarfs, small, cool, and dim. Their habitable zones are huddled extremely close to the star. Being that close creates a strange effect, tidal locking. The planet's day and year become the same. One side always faces the sun. On a tidally locked world, one half is a permanent furnace of light, while the other is a forever frozen night. Life would be a struggle. Our best hope for life there would be the Terminator line, the thin strip of eternal twilight between day and night. A cosmic ring of spring. But temperature isn't everything. A planet needs a magnetic field to protect its air from solar winds. Without it, the atmosphere is stripped away. Imagine the atmosphere as a warm blanket. If the star is too violent, it rips that blanket off, leaving the world naked and dead to radiation. And don't forget plate tectonics. Geologic activity recycles carbon, keeping the climate stable over billions of years. A planet needs a heartbeat. When we find a world that has water, a magnetic field, and a geologic heartbeat, we've found a candidate for Earth 2.0. Which brings us to the most famous neighborhood in the galaxy. 7 Earth-sized worlds, all huddled around a single dim red star. Welcome to TRAPPIST-1. It's time to see if any of these 7 sisters are breathing. Just 39 light-years away, a blink in cosmic terms, lies a star system that looks like it was plucked from a science fiction novel. TRAPPIST-1. The star is an ultra-cool red dwarf. It's barely larger than Jupiter and only 2,500 degrees, cool enough that its planets can huddle incredibly close. In 2017, NASA announced something historic. This system has 7 rocky, Earth-sized planets. All of them closer to their star than Mercury is to our Sun. Because the system is so compact, if you stood on one planet, the others would appear in your sky as large as our Moon. A sky full of worlds. But the real excitement is here. Planets E, F, and G, all 3 sit right in the star's habitable zone, where liquid water could exist. TRAPPIST-1e is the most promising. It's almost the same size as Earth and receives about the same amount of starlight. It could have oceans. However, life here faces a challenge. These planets are tidally locked. One side is a permanent day, the other a permanent night. The constant heat on one side and cold on the other would create massive, eternal winds. A storm that never ends. Scientists are now using the James Webb Telescope to look for atmospheres. Does TRAPPIST-1b have air, or is it just a naked rock? Red dwarfs are notorious for violent flares. One big burst could strip a planet's atmosphere in a few million years. Radiation is the enemy here. To survive, these planets would need strong magnetic fields, like Earth's, to act as a shield against the star's temper. Even if life is rare, the TRAPPIST-1 system gives us 7 chances. 7 independent experiments in planetary evolution. What if we find oxygen? Or methane? What if we find the chemical signatures of a living world on one of these sisters? TRAPPIST-1 isn't just a system, it's a target. A laboratory that will finally answer, is life common, or are we a cosmic fluke? But our hunt doesn't stop at 39 light-years. We are aiming further, searching for a mirror of our own home. Earth 2.0. To find life, it's not enough to see a planet. We need to smell its air. And for that, we built a hunter with golden eyes, the James Webb Space Telescope. Webb uses a technique called transmission spectroscopy. As a planet passes in front of its star, some of the starlight filters through its atmosphere. The gases in that atmosphere absorb specific colors, leaving dark gaps in the spectrum. These are chemical fingerprints that Webb can read. In 2022, Webb achieved a historic first. It detected carbon dioxide in the atmosphere of the gas giant WASP-39b. We were literally tasting alien air. WASP-39b is a hot, puffy planet. Because it's so large and its air is so thick, it was the perfect first target to prove Webb's incredible precision. But gas giants are just the beginning. The ultimate goal is to find biosignatures, the chemical smoking guns that prove life is present. Oxygen alone isn't enough, it can be made by stars. But oxygen combined with methane? That almost always means something is breathing. In 2023, Webb looked at K2-18b, Hycean world, a planet with a massive ocean and a hydrogen-rich atmosphere. It found methane and CO2. K2-18b is twice the size of Earth. If it really has an ocean, it might be the first time we've seen a habitable liquid world outside our own. But Webb has more work to do. It's now staring at the TRAPPIST-1 sisters, trying to see if they have lost their air to the red sun's flares. Early data on TRAPPIST-1b suggests it might be a bare rock, with no atmosphere at all. The hunt for a living atmosphere is proving to be hard. But we aren't giving up.
Wow.
Webb is just the first in a new generation of telescopes designed to find the signatures of an alien biology. Soon, missions like the Habitable Worlds Observatory will go even further, directly imaging Earth-sized planets for the first time. We are no longer wondering if planets exist. We are now asking, what are they like? And who, if anyone, is breathing there? The hunt for Earth 2.0 is nearing its climax. Let's imagine what we will find when we finally arrive. We have the coordinates. We have the mass and the distance. But numbers don't tell the whole story. If we could land on Earth 2.0, what would we see? First, the sky. If the planet orbits a red dwarf, like Proxima b or TRAPPIST-1e, the Sun would be a giant, deep red orb that never sets. The light would be softer, warmer, and more orange. And because of the planet's orbit, your shadow might never move. It would be an eternal evening. Life would adapt. On Earth, plants are green to absorb sunlight. But under a red sun, they might be deep purple or even black to catch every bit of energy. Imagine a forest of obsidian trees under a crimson sky. It sounds like a dream, but it's a very real scientific hypothesis for photosynthesis. The oceans would be different, too. If the planet is tidally locked, the gravity of the star would pull the water into one massive, permanent bulge. At the terminator line, the boundary between day and night, vicious storms would howl as hot air from the sun side meets the frozen darkness. Gravity might be stronger or weaker. On a planet twice the size of Earth, you would feel twice as heavy. Every step would be a struggle. Our fox friend here would need stronger muscles and denser bones just to stand up. The very shape of life is dictated by the mass of the world. But what about the air? We might find worlds with nitrogen like ours, or strange, Hycean, worlds with thick hydrogen atmospheres and warm oceans. On some exoplanets, it might not rain water at all. It could rain liquid methane, or ammonia, creating lakes that would be toxic to us but home to others. The most speculative part is the light. If we see a planet with city lights on its dark side, it would mean we've found more than just a home. We've found a civilization. A neighbor. Another mind in the dark, looking at their own telescopes, wondering about us. Whether it's a quiet rock or a buzzing civilization, Earth 2.0 is out there. It's no longer a matter of if, but when. As we reach the final act of our journey, we must ask, what does all this mean for us? For a small species on a pale blue dot? Our journey began with a simple question: are we alone? For 30 years, we have been building the answer, brick by brick, world by world. We now know that every star in the sky likely has a family of planets. 2 trillion galaxies, each with hundreds of billions of stars. In 1961, Frank Drake gave us a formula to estimate the number of civilizations. Today, we finally have the data to fill in the first few lines. If only 1 in a million habitable worlds develops life, and 1 in a million of those develops intelligence, the galaxy is still crowded. But where is everyone? This is the Fermi paradox. If life is common, why haven't we heard a single hello in the radio waves? Perhaps there is a great filter, a barrier that prevents life from surviving long enough to reach the stars. Is it behind us, or in front of us? Maybe we are the first. Maybe we are the early birds of the universe, and the billions of other Earths are still waiting for their time. When we finally find Earth 2.0, it will be the most significant moment in human history. It will be the end of our cosmic childhood. We will no longer be the center of the world. We will be a single citizen in a vast, living biological community of the cosmos. Finding others doesn't make Earth less special. It makes life itself more precious. It means the universe is not just a collection of rocks. It is a garden. And we are just starting to realize how big that garden really is. We are finally ready to meet our neighbors. The hunt for Earth 2.0 is the hunt for ourselves. It is the quest to find out if the miracle of life is a cosmic rule or a lonely exception. So, keep looking up. Because someone, on a world we haven't named yet, might be looking through their telescope, asking the same question. And maybe, just maybe, they are looking right at you. I'm your cosmic guide, the Fox. Until next time, stay curious.